Hey, howdy everyone. I'm Michael Perch. I'm an associate professor at the University of Texas at Austin, where I teach and conduct research in data analytics, geostatistics, and machine learning. Now, I share all of my university content online to support my students with evergreen content and to support working professionals, and maybe also to encourage other folks to go into STEM, science, technology, engineering, and mathematics. I would love to see that. So this is part of my continuing data science basics in Python series. It's live code. There is a walkthrough. If you want to join in, all you have to do is go to my GitHub account. And then what you'll do is you go to my repositories right here, Python numerical demos. And there are many demonstrations in Python of data analytics, machine learning, and geostats. Go all the way down to Python Data Basics. Look for Bootstrap. Open that up. You'll get the same thing that I'm showing right here. All right. Go ahead. I'd love to see you join in and follow along. Let's get started. Bootstrap and Python. It's a very simple workflow I'm going to demonstrate for Bootstrap for modeling workflows. This should help you get started with important data analytics methods to evaluate and integrate uncertainty for any statistic, but also for any model. And I'm not going to get into this, but the concept of Bootstrap, of course, is used in machine learning for the purpose of ensemble modeling. Not going to talk about it. Bootstrap gives us uncertainty in a statistic. One source of uncertainty is data paucity. We just have too few samples. And the question is, do our n samples provide us with a precise, accurate estimate of, well, what's the statistic we're working with? The mean, standard deviation, skew, the 13th percentile, it doesn't matter. But we want to know how certain we are given that limited sample size. What is the impact on uncertainty in the mean of, say, porosity if we were to add more data? We want to be able to use this methodology to be able to empirically calculate standard errors, confidence intervals, or even for conducting hypothesis testing. You name it, you can do it with Bootstrap. In fact, what I tell my students is you can bootstrap everything. Bootstrap is a method to assess uncertainty in a statistic by repeated random sampling with replacement to create multiple simulated data sets. So does Bootstrap work? I wouldn't blame you if you heard what I just said. All we're going to do is repeated random sampling with replacement from a data set and get the uncertainty. Doesn't seem like it should be able to work. It turns out that when you use the procedure and you compare it to cases for which we have the analytical solution, we find, in fact, that it does work. You can prove it for yourself. In fact, you could do Bootstrap on the mean, and we're about to, and you could go ahead and look at the standard deviation you get of the resulting distribution of the samples, the realizations of the mean. We'll talk about that. And you could compare it to the standard error, the analytical solution for what we'd expect for the variance or standard deviation. Take the square root, and you'll find it'll actually match. It actually does work. We'll even show the entire distributions, the student t distribution. Extremely powerful, could calculate the uncertainty in any statistic, you name it, you can do it. Would not be possible to assess general uncertainty for any statistic without the Bootstrap. We have analytical solutions when it comes to various statistics, but not in all generality. And what I teach my students is you could even come up with your own statistic, and you could Bootstrap that too. Advanced forms are available to account for spatial information sampling strategy. An example of that is Germelian Spatial Bootstrap, original publication in 1993. I do have a demonstration workflow in Python of spatial bootstrap. I'm a big fan. I think it's very powerful. Here's the Bootstrap workflow. We're going to assemble a representative sample set, or we could build a cumulative distribution function using available analog information, and you could even account for declustering, representativity, sampling bias, and so forth. I have other workflows that demonstrate how to do that. Then for L equals 1 through big L realizations, do the following. We'll do n samples with replacement from the sample set, or we could do Monte Carlo simulation from the CDF. Effectively the same thing. Then we could go ahead and after we've done n samples, that gives us a new realization of the data set. we can now calculate a realization of the statistic from this realization of data set. So that becomes our realization, whatever the statistic is, means, variance, doesn't matter. Then we repeat over all the L realizations. We'll go ahead and compile and summarize the L realizations of the statistic, and that's it, we're done. That's our uncertainty model for the statistic. This is very powerful. Let's try it out, but first, let's talk about the assumptions and limitations. First of all, representativity. Samples are sufficient and represent, if you're working with 7 data or less, or even 12 or something, you don't do this. You don't have enough samples to really know the data distribution. And if the samples are biased in the samples will result in bias in the uncertainty model. The bias is going to be transmitted right through. Stationarity. The metric of interest is invariant under translation. If you're working with spatial data, you're assuming it's the same everywhere. This is the identically distributed part of IID. No spatial context. Independent samples. That is the I part of IID. There's no correlation between each one of the data values. Does not account for the boundary of the area of interest, any local information sources you may have. Nope. There's no spatial context whatsoever. If you want spatial context, we need to use spatial bootstrap, the Journalian method I mentioned before. Uncertainty source. It only accounts for the uncertainty due to too few samples, and that is not the only source of uncertainty. No, not for our spatial data. We have all kinds of uncertainties related to the fact that there is non-stationarity. Multiple populations are being mixed together. Measurement errors. Interpretations of the data. There are so many sources of uncertainty. This is only capturing the component related to sparsity, or I should say paucity of the data. What's the project goal right here? We're going to learn the basics of working with Bootstrap for uncertainty modeling in Python. We're going to use this to be able to build practical data analytics, geostats, and machine learning workflows. Now, a couple of caveats before we get started. I have included methods that I found useful for building my science, geoscience, engineering workflows for the subsurface. I have aimed to be accessible for most scientists and engineers. I could have been more complicated, but I'm trying to keep it very basic, in other words. There are more advanced, more compact, better coding methods to accomplish the task. See the first point. I tried to keep things very simple and accessible, and I do appreciate feedback, and I will use that to improve future workflows. So let's go ahead. This is a live code demonstration. We're running it together right now. We're going to load and configure the required libraries, Python packages to work with. NumPy for working with ND arrays, pandas for working with data frames, the data table that we're going to load, OS so that we can set a working directory, matplotlib for our plotting. Those are the main ones that we'll be working with, but we have the others here. We'll run that code right there. Now we have that available. Let's go ahead and build some convenience functions for plotting. I like having concise, readable code. And I find, to be honest, when we do plotting in Python, it's very easy to have big, long blocks of code just to build a single figure. What I like to do is tuck that into a function so we have really nice, concise workflows afterwards. We're going to have custom histogram, not a big deal. It takes matplotlib's hist function, builds a histogram, and just adds summary statistics and I think some intervals on it and so forth, vertical lines. Custom histogram with uncertainty is going to give you that histogram, but it's going to actually show the Bootstrap uncertainty. You see, this is live code. The Bootstrap uncertainty model superimposed, and display Bootstrap will display the Bootstrap realizations histogram with the analytical or just a kernel density estimated PDF, just to give you a sense of what that distribution looks like. Everything is about concise, readable workflows. Let's go ahead and just run those functions so they're available, as I mentioned before. So we go ahead and run that block of code. Now we have those functions. We're going to be working with Monte Carlo simulation. It's going to be based on a random number generator, which will have a seed. If you don't set it explicitly, it will be set usually by the computer time or something like that. By setting it explicitly, we can ensure repeatability. When I run this, you run this, everyone runs this, we get the same thing. The problem is this: when you set the seed, every time you call for another random number, you're going down that series of random numbers from that random number generator for that seed. And so if you run one of the blocks of code that I have multiple times, you'll get out of sync and you'll have a different response in subsequent runs. So what I've done is many times I set the seed in each block to ensure that we all have the same output. Not a big deal. Let's go ahead. This is how we do it. It uses random, which is a built-in library to Python, standard Python. And there is specifically a seed function which allows us to set the random number seed. Okay, so we can go ahead, we'll set my favorite lucky number 13. We'll go ahead and run that block of code and we're done. Now we'll set a working directory. I often do this in workflows because I'll often be loading and saving, and I'll have multiple steps in my workflows, and I can possibly create a lot of intermediate files in my workflows. And so I like to explicitly control the current working directory as I go along to make sure that I know where things are going. I don't lose them, and I like to avoid having to include the full address every time I write or read a file. So we'll go ahead and we'll set the working directory so that when we do write out some outputs, we'll know where it is. And if you load my data set onto your computer, you know where to put it. Here's where we're going to go ahead and load the tabular data. This is part of I have a repository with a lot of data sets that are available for people to experiment with. I use them for the purpose of my teaching and all of these demonstrations that I've shared. GeoDatasets repository on the Geostats Guy account on GitHub. So go ahead and you run this block of code right here, you'll load it. Now, if you've downloaded that to the working directory, you can go ahead and use this code and just load it from the working directory. Go ahead and we'll do some really basic feature engineering. Let's drop some of the samples. Now, this is not standard feature engineering, to be honest. This is simply for educational purposes. By decreasing the number of samples, we're going to see wider uncertainty. You can come back and increase the number of samples, i.e. the fraction of data retained. Right now it's 10%. And you can go ahead and see how that changes uncertainty. Running this line right here, we'll go ahead and scale the porosity by 100 to convert it from fraction to percentage. So if you run this block of code right here, you'll see we're now working with 29 samples, kind of a small number of samples, but it'll be interesting to observe. Let's go ahead and see what our data looks like. And we look right here, we'll see that we have an index, we have X, Y, facies, porosity, and permeability data available to us. This is what our data frame looks like. I have lots of other workflows where I demonstrate working with tabular data with data frames. You can go ahead and check that out. We'll calculate some summary statistics. Just to explain here, we have X and Y coordinates in meters. Facies 1 and 0. 1 is sandstone, 0 is some type of interbedded sand and mudstone. We have porosity in a percentage. We just changed it to a percentage before this, so let me just go ahead and update that right there. And we have permeability as in millidarcies. So what we'll do next is we'll set a few variables to support our plotting, the extents for all of the features of interest, X, Y, locations, the coordinates, the porosity, permeability, and we'll set a color map. This is just all very basic things just to assist us with plotting. I like doing that because then if I want to go back and change the extents, I change one place and all my plots update. Next, we'll just declare a couple more things. This is very simple, just for concise, readable code. And so we don't have to say data frame and extract the series porosity and convert it to a 1D array every time I want to do something with it. Let's just go ahead one time and we'll get a one-dimensional ND array called por. And we're going to need to do a bunch of plotting, for which we're going to need a set of values along the range of porosity values. And so we'll go ahead and do that with NumPy's linspace once. LPOR is going to be a sequence of values from the minimum to maximum porosity value, 100 values equally spaced. That'll help us with all of our plotting. We'll go ahead and run that. We've got that done now. Then we're going to do some basic visualization. Not a big deal, just a good idea to take a look at our data. Location maps, histograms, scatter plots. For the live code walkthrough, I made a really silly function. This is just so I can build this right here and then go to the next slide, and there you can see the plots. Otherwise, with the code and the plots, it all doesn't fit. So we can just take a look. We have spatial data, porosity, permeability, the relationship between porosity and permeability, the histograms of each. So a basic look at the data. I have much more information about bivariate and univariate data visualization in other sections. We're not going to spend time on this, but just to get a chance to see the data. Bootstrap pseudocode. What does the code look like? What we do is we would specify the number of bootstrap realizations, L. We would declare a list to store the bootstrap realizations of the statistic we're calculating. We would loop over L equals 1 through L bootstrap realizations. There's going to be a loop. We'll do N Monte Carlo simulation, random samples with replacement for a new realization of the data. We will calculate the L realization of the statistic from that realization of the data, and we would append that to this list. Repeat, repeat, repeat. We'll get L values, realizations of statistic. We'll return it. That's what our function should look like. Let's go ahead and make that function. Let's make the world's simplest bootstrap function, but it's going to be very flexible. Its arguments are Z data is a one-dimensional ND array with the original data set. N real is going to be the number of bootstrap realizations to calculate the L that I showed before. Stat is going to be a function. We're going to pass a function that calculates the statistic of interest, and then our function is going to return Z or Z real, a list of N real realizations of statistic stat. Okay, so this is what the code looks like right here. It reads in the data set as a one-dimensional array, number of realizations. We're going to use stat. First, it creates an empty list. Looping over, it calculates a random set. Fortunately, the random built-in library in Python actually does provide us with choices, which will do Monte Carlo simulations or sampling with replacement from a list of values. And we just tell it, I want K values with replacement, which is going to be the length of the data set. So give me back the same number back, but do it with a replacement so I don't get the exact same data set back. Then I calculate the statistic of interest on that realization. I append it to the list, and when I'm done looping, looping, looping over all of the N real, I can return the list of realizations of the statistic. Let's run that. We now have our function. Now, anybody there who is an expert, has done a lot in this area, will know immediately that SciPy and other packages do have Bootstrap functionality. But I thought, wouldn't it be super cool to just write our own? Look how simple it is. Now, of course, there's better functionality available in their methods, but this gives us the basic methodology. Now let's demonstrate Bootstrap for uncertainty of the mean. The reason we start with the mean is because in this case, we know the analytical solution. We can compare the Bootstrap samples and their distribution and their summary statistics to what we would expect from the theory. And the theory is that we should be able to calculate any confidence interval of the mean as being the sample mean plus or minus the student t distribution for percentile alpha level divided by 2. So we want the confidence level of the 95%. Then we're going to be talking about working with the percentile of 2.5 and 97.5. So we have the alpha outside on the tails, and the degrees of freedom is n-1, and the standard error, the standard deviation, because remember, this student t distribution we're parameterizing here is a standard one. In other words, it has a mean of 0 and a variance of 1. Well, we can expand the standard deviation by the standard error, which is given to us by theory. Well, another way to express this is that the distribution we expect should be equal to the student t distribution of this many degrees of freedom scaled by the standard error or repositioned by the sample mean. And so we know what the analytical expression should be for the confidence intervals and the entire distribution. Let's see if Bootstrap does it. What are we going to do? L, the number of Bootstrap realizations of the mean. We're going to set the random number seed, Bootstrap our function. We're going to pass into it the porosity list of values. Remember the 29 samples. L, that's the number of realizations. NP, NumPy has a method to calculate an average from a one-dimensional array. We just pass it that as our argument. That's our function. And we run that, and what comes out is going to be a list of realizations Bootstrap for the mean. And then we can go ahead and use our plotting functionality. Let me go ahead and run that, and then I'll explain what we got. This is the original porosity histogram right here. We already did this. We showed the summary statistics, including the histograms. This is the average standard deviation, P10, P90. I like doing that. I like some summary statistics on my plot. The dotted line is just the average, not a big deal. This is important because we want to show that Bootstrap is going to be unbiased. Here's the Bootstrap realizations of the average. Isn't that cool? So we can see this histogram it's the actual empirical result from Bootstrap. Now, first of all, let's observe this. The average is equal to the average of the original data. It's unbiased. It's not shifted. You should see that if you have enough samples. We can also see the uncertainty in the dispersion, the spread. And I have denoted P10, P90, which many organizations use for planning purposes. That's fine. Now, if you look really carefully, you'll see a gray line. The gray line is the analytical expression. It is a student's t distribution with degrees of freedom n-1, scaled by the standard error shown right here, and shifted by the actual sample mean. Okay, so we can see that the histogram closely matches, the histogram from Bootstrap closely matches the analytical without you having to memorize the analytical equation or know the theory behind it. Really, you're able to go ahead and just run the Bootstrap methodology. Very powerful. Bootstrap uncertainty, well, we'll go back and show the histogram, we'll show the mean, and we'll show the uncertainty P10, P90 superimposed on top. Not a bad idea to just show that, communicate that. This has been an example of Bootstrap and the mean. Now, often you need to move it outside your workflow to work in another platform to be able to get the job done. I just want to demonstrate to you that that's very easy. Set a file name, feature name, create a data frame with that list of realizations. Go ahead and use the built-in functionality for Pandas data frames to write it directly to a flat ASCII comma delimited file or space delimited or tab delimited. You can write it to any type of format. Here's comma delimited. And when we're done, this is what we've written out. Average porosity, we have the realizations 1 through 1,000 or so, and they've now been written to a file. We can load up that file, we can run it elsewhere, we can do anything we want. Okay, I thought that was good to just demonstrate that. We're not stuck in your Python workflow. Often, in fact, if I have many workflows, I may save that data file and then I have another workflow for doing additional steps. I'll load the data in. Or sometimes your workflow takes time, and so I like saving out data files so I don't have to run the whole workflow every time I start. Okay, now this is fast though, of course, right? Let's demonstrate Bootstrap for uncertainty in the standard deviation. You can bootstrap any statistic. That's what I said. L equals 1,000, random number seed, so we all get the same result. We're going to go ahead and run the Bootstrap function porosity with the data list, L 1,000, and NumPy has the standard deviation calculation. It'll calculate standard deviation on one-dimensional array. So that's perfect. We go ahead and run that. We get a list of standard deviation realizations. Now we can go ahead and display them. We'll use that nice display function and take a look. I'm not going to do those other plots anymore. Let's just look at the uncertainty distribution. From now on, all I'll do is go ahead and just use a kernel density estimate of the statistic realizations to get a nice fit PDF as shown right here. So not a big deal, really straightforward. You can see the average. If you check back, you'll see that that's equal to the sample standard deviation. And we have the uncertainty, the P10, 2.9, the 2.9, the P90 around 3.9 right here. And so you can see the overall uncertainty in the standard deviation due to the fact that we have too few data. Now go back for fun. I'm not going to do this. Change the number of data, try rerunning that. And you'll see it'll change. What do you think? If you increase the number of data, the uncertainty will go down. That makes sense. Okay. Let's go ahead and do something more complicated. Sometimes we work with statistics derived by multiple other statistics. The coefficient of variation is a great example of that. It's equal to the standard deviation divided by the mean. Okay, when I do this with students, they get very confused because what they try to do is they bootstrap the standard deviation, they bootstrap the mean, and then they try to put it together somehow. Nope, that's not what we do. What we do is every time we bootstrap, we get a new realization of the data set. So don't stop short. Calculate the mean, calculate the standard deviation realization from one data set, and then finish up with the coefficient of variation realization for that same data set. Okay, don't stop short. So in other words, for the coefficient of variation, we'll calculate bootstrap realization of the data set with n samples with replacement. We'll calculate the mean and standard deviation of the bootstrap realization. We'll calculate the coefficient of variation from those. That will become the realization of the coefficient of variation for that one realization of the data set. Now we repeat this L times on L realization of the data, and we can then evaluate the distribution that results. So let's go ahead and do that. We're going to, this time we'll make a lambda function. We'll just demonstrate that really quickly. Our lambda function is going to take x, calculate the standard deviation, calculate the mean, and divide them. This is the coefficient of variation being calculated from the one-dimensional ND array, whatever it may be. That's our function we can pass to our bootstrap function. So now we have porosity list of values, L number of realizations, 1,000 again, and our custom lambda function for coefficient of variation. And we can go ahead and run that and visualize the result. Look at that. That's pretty cool here. We've calculated the average standard deviation. Isn't that cool? Standard deviation of the coefficient of variation. In other words, its dispersion or its uncertainty. P90 and P10, we can see right there. We could, of course, change the number of decimals. I apologize for this. I just didn't feel like adding more complexity to my plotting, but not easy enough to add that in. All right, so that's coefficient of variation, and it's teaching us that you don't stop short with Bootstrap. You get a realization of the data, you get a realization of statistic, go right to the final calculation of that statistic for that realization of the data. Let's demonstrate Bootstrap for uncertainty interquartile range. That's another example of a statistic that's derived from two other statistics. Interquartile range is equal to the P75 minus the P25. SciPy stats module has a built-in function for interquartile range from an array of values. So we can go ahead and use that, pass that through, and look at that. So easy. And we've got the result right here. The average, the standard deviation, the P90, the P10. Now, this is really good because it illustrates something. And that is, do you see kind of the almost multimodal type of behavior? Some statistics are going to be more sensitive to extreme values. Bootstrap may cause what appears to be multi-mode. It's because we're working with a relatively small data set, and there may be one or two values that are very high, very low. If we don't include them, it'll result in one response. If I include maybe one of the high values, it'll kind of shift it. If I include high values, maybe two of them, or that same high value twice, it'll shift even higher or lower, depending on the statistic. This multimodal looking behavior is caused by that type of sensitivity. Let's go ahead and we'll do one more like this. Let's do percentile. Percentile case, we do have a function that can calculate percentile, numpy percentile, but it does need an argument, and that argument is the actual percentile you want to calculate. So what I do is I just define my own function, my percentile, with the data, and I specify which percentile. I hard code it effectively. Now I can go ahead and I can pass that function as the statistic using the same pattern we did before, without any other complexity in our code, keeping it simple. And we can go ahead and calculate the uncertainty in a percentile. So this right here is the uncertainty in the 50th percentile. We can go ahead and rerun it. That's the uncertainty in the 10th percentile. We could rerun it. That's the uncertainty in the 90th percentile. You see how it's changing? We're bootstrapping the P50, the P10, and the P90. You can bootstrap anything. So powerful. I love Bootstrap. Now we got one more example here that I want to show you. And this is the example of the uncertainty in a proportion. Now we're going back, we're closing the circle back to a method for which we have an analytical solution. The confidence interval in a proportion is going to be the estimate of the proportion, sample proportion plus or minus the student t-distribution, alpha level divided by 2, degrees of freedom, and minus 1. This is just like we did before, but the standard error calculation is the sample proportion times 1 minus the sample proportion divided by the number of samples, all of that square root. Okay, so that's going to be the standard deviation of the resulting sampling distribution, the standard error. And the entire distribution therefore can be described as the student t-distribution with n-1 degrees of freedom, which is standard in the fact that it has a mean of 0, variance of 1. So we can go ahead and expand it, squish or squeeze it by the standard error, and we can shift it by the estimate, the sample proportion. This is the distribution we expect. So we have the analytical expression for what this should turn out. And we do have facies in our data set, so we can try an uncertainty in the proportion of sand and, what was it, sandy shale or something like that. Now, this function, this is going to be kind of a long, ugly function. I'm not going to walk through it or spend time on it, and I've done a terrible job. In fact, I could have done a much better job to factor the code into distinct functions that work together. I could have done a better job generalizing the code, but we'll go ahead and just run this. It's not great, but it'll get the job done. Okay, so here we go. We have our methodology proportion, Bootstrap with visualization cooked in. We feed into it the list of facies, zeros and ones. It's hard coded for that too, so you can't use this for any general case. Number of realization, number of bins for some of the plotting we're going to show. And what it'll give you is the realizations of proportion of sand, proportion of shale, and we'll also have the plotting. Okay, so when we're done, this is what we got. The original data, proportion of shale was 10%, proportion of sand was 90%. That's how we started. Now with the 29 data we're working with, this is the distribution of the uncertainty in the proportion of shale, centered around 10%. That makes sense. The expected value is 10%. Good, unbiased. This is the uncertainty distribution sample from Bootstrap for proportion of sand. It has the right expected value for proportion, unbiased. That's good. The lines right here are the student t-distributions, the analytical expression for the uncertainty in proportion given that data. And I hope you can see it hasn't done too badly. In fact, if we were to run many realizations, we should find that it should converge quite well. All right, so this is uncertainty in the proportion. Now, like we did before, you may want to write out your results. I just want to show it to you again. We could go ahead and put them both together into one data frame with proportion of realization proportion of sand, realization proportion of shale. They'll be complements of each other. And we'll go ahead and create a data frame and then write that out as a CSV file. Not a big deal. If you want to go ahead and see what that looks like, you could go ahead and add a head command right there, and you can see it right there, and we can commit ourselves that those realizations are complements. Now, don't be too disturbed by their similar numbers between realizations. What's going on there with the number of data you have, there's only so many proportions you can actually get. I hope you can see that in one realization you might have 3 shale and 26 sand, or 25 sand and 4 shale, or something like that. So there's only certain discrete proportions you can actually see with that size of data set. All right, this has been a demonstration of Bootstrap in Python. I think this is a very powerful methodology. It's going to empower your data science workflows. Remember, you can use the Bootstrap to calculate uncertainty in any statistic. You're calculating realizations as statistic, representing uncertainty due to sample paucity. There is assumptions in Bootstrap, including stationarity and representativity of the data. And remember that you get a data set realization by Bootstrap and you calculate the statistic on that data set realization. If your statistic is derived from other statistics like interquartile range was, you go right to the end, you don't stop short. You get a realization of that on that realization of the data set. I have many other Python data analytics and machine learning demonstrations that I share. You can see an inventory on my website It includes my YouTube channel with all my lectures, my GitHub account, and so forth. I am Michael Perch. I'm an associate professor at the University of Texas at Austin, where I work, conduct research, and teach on data analytics, geostatistics, and machine learning. I'm happy to discuss anytime. I hope this has been useful to you. Thank you very much.